All right, today we're going to cover Riemann sums, which is topic 6.2 in AP Calculus. And don't worry too much about the word Riemann right now. You need to be more interested in the word sums. And we've got a picture here, a continuous function bounded by this function f of x. And we're looking at it from a to b. And what you've seen here is that there's some rectangles drawn. What we did in topic 6.1 was we just kind of found areas under the curve a little bit the best we could. But we can be more exact if we start dividing these things up into rectangles. So for example, I square this off. And on this next one, I square it off. And so on. And I square this off, and I square that off, and I make these each an individual rectangle, all right? Well, the problems that you see will tell you how many rectangles. When you see this number of subdivisions, it is how many rectangles we're talking about, all right? And it makes sense that if we're going from A to B, that distance is B minus A. And it also makes sense that if I wanted to know the width of each one of these rectangles, we'll call that delta x, which we've got labeled right here. If I wanted to know the width of each one of those rectangles, I would take the total width, B minus A, and I would divide it by the number of rectangles, which we will call n. All right, so for example, if I was going from 3 to, let's say, 13, and I wanted 5 subintervals, for example. Well, that means 5 rectangles. All right? I can find the width of each rectangle by doing 13 minus 3 and dividing it by 5. So that's 10 divided by 5, which is 2. So I know that each of those rectangles in here, each rectangle, 1, 2, 3, 4, 5, would have a width of 2. Now, when we find the area of a rectangle, don't we do length times width? We do length times width. What's the length of each individual rectangle? The length is the function value at that, we could say that x-coordinate. Now, there's all kinds of fancy notation that we can use for this. You know, we could say that this x-coordinate right here is x sub 0, all right, for example. And so if I wanted to know the length of this rectangle right there, the length would be equal to f of x sub 0. It would be the function value. All right? So that's kind of an introduction to what we're doing here. And then what we do is then, you see the word sums, we're going to add up all of the rectangles. We're going to add up, we're going to add all the areas. So let's look at one, a kind of a sample problem here. This one is a numerical problem, and the reason that it's numerically is because we have unequal widths. Okay? So g of x is a continuous function from 0 to 25, where g of x is the rate that Catherine travels from home to school. G of x is in meters per minute, and x is in minutes. Let's find the distance that Catherine travels. Remember, if I find an area under the curve of a rate, I'm going to go back to a position type answer, a location type answer, all right? So we're doing this using here's the word left, Riemann sum. Let's go back to our picture from the first slide. When we talk about using a left Riemann sum, we are using the length from the left edge of the rectangle. So we would use that length for that rectangle. Then on the next rectangle, I would use the left edge again. That would be my length. So when we talk about a left Riemann sum, we are using the left edge. So, really what we're doing is we're looking at how many rectangles here? Well, I have a rectangle here. All right. And let's just kind of take these individually for a second to get us started. What is the width of that rectangle? The width is 2. All right. What is the length? The length is the left edge of the rectangle, which will be this one. So the length is 10. So we have 2 times 10, which is 20. And that's the area of that first rectangle. Then we go to the next one, from here to here. What's the width of that one? I think everybody sees that it's 4. The length of that one is, again, the left edge, which is 14. 4 times 14 will give me the area of that one. That's 56. Remember, we are going to add all of these together when we get done. And so we just keep working through our problem here. This one's going to be 2. I can go a little bit faster now. 2 times 20, which will be 40. This one, notice, has a different width. This one is 7 times the left edge, which is 15. That's 105. That's a plus. This one is 5 times the left edge, which is 30. So that's 150. We're adding that one on. And the last one has a width of 5 times the left edge, which is 20. So that's 100. And then we add all of those numbers together to get our answer. So we can grab the calculator if we want to do that. I'm grabbing mine handheld calculator. 20 plus 56 plus 40 plus 105 plus 150 plus 100, and we get 471. Now we're talking about how far did she travel? Well, it's miles. All right, and we did that with again, a left Riemann sum. Left, which again is using the left edge of each rectangle for our length. All right. Now, we could have one where the widths are an equal width. These are a little bit cleaner, a little bit faster. All right, find the area of the region using a left Riemann sum bound by the function h equals e to the x. Okay, here's our function e to the x. We're bound by from 1 to 3. Boom, boom. And we have 6 subdivisions. That means 6 rectangles. So if you remember what I told you, to find the width, the width, which we call delta x, change in x, is going to be 3 minus 1 divided by 6. So that's 2 divided by 6, that's 1/3. All right, so I have 6 rectangles in here. See if I can do this. 2, 3, that's the 4th one, 5th, and the 6th one. The width on each one of these is 1/3. All right? The width on every one of them is 1/3. But what am I using for the length? The length is, once again, the left edge. So what is the left edge? On this first one, the left edge is f of 1. So on this very first rectangle, f of 1 will be e to the first. And that is the length of the first one. So the very first rectangle, okay, I will call this R1, is going to be e to the first times our width of the rectangle, which is 1/3. Our second rectangle is still going to have a 1/3. As a matter of fact, all 6 of them. 1, 2, 3, 4, 5. All 6 of them have a width that's 1/3. All 6 rectangles. And we're going to add all these together. All right? So that's why we're told that we could do this algebraically. I'll get to that in just a second. But what are these other lengths? Well, they're going to change. This length is now going to be 1 1/3, which is 4/3. So this is going to be e to the 4/3. And the next one is, so this one is 4/3. The next one is, this x value is 5/3. So this length would be e to the 5/3. All right. Then we're up to e to the 6/3, which is e to the second, e to the 7/3 power, and e to the 8/3 power. All right, so there's our 6 rectangles, and then we add all these up, add together. Now the reason we said we could do it algebraically, I'm not sure there's a huge advantage to doing it algebraically, is I could pull, you see there's a 1/3 in all of these, I could do a 1/3 times the sum of all those function values. E to the first times e to the 4/3, I'm sorry, plus, these are all pluses, plus e to the 5/3, plus e to the 6/3, etc., etc. I could add up all those function values and then multiply by 1/3. All right, I'm not sure if there's an advantage to doing that or not. I suppose you could find all those values in the table on your calculator and go from there. So, just to summarize again, a left Riemann sum, we are using the left edge to find my length. So this rectangle would be that left edge. The next one is a little bit down from there. So on. And we just keep going. We're using the left edge to find our length. All right? So if you notice, this function here on the left is concave down. All right? This one over here on the right is concave up. And you'll notice on this one over here, my rectangles, since I'm using the left edge, these would be an underestimate. These would be an overestimate of the actual area. Now, if we go to a right Riemann sum, if let's say that we're doing a right Riemann sum, it just means we're going to use the right edge for my length. That's a right Riemann sum. We're going to use that length, we're going to use this length, we're going to use this length, and so on. Okay, that's for a right Riemann sum. That's the only thing that changes. Okay. If we do the midpoint, however, if we're doing the midpoint, we're actually looking at the function value that is at the midpoint, I'll try to draw it in there, of the rectangle. All right? So the midpoint takes a little bit longer because we actually have to take the first function value and the second function value. Let me label those as f of x sub 0. The first function value and the second function value of the rectangle and divide them by 2. That's going to be the width of each individual rectangle. And doing it by hand requires a little bit more work because we are working with 2 function values. It's still the same process. We're still doing area equals length times width. But now my width is an average of those 2 function values. So, if they gave you this problem, this is the problem we just did. And they said, find the area using a midpoint Riemann sum. I'm going to draw my graph a little bit bigger this time. Here's 1, here's 3. We're still doing 6 equal subdivisions, all right? So I do know that my width is going to be 3 minus 1 divided by 6, which we know is 1/3, all right? Well, that's what would be the regular width. That's not going to change. But what changes is when I do my calculation for my length, let's just look at, this is going to be 4/3, this is going to be 5/3, this is going to be 2, and so on. Let's say that I wanted to find this rectangle right here. I'm going to use this midpoint, which comes up here and is halfway, and that's what I'm going to use for my rectangle. And that midpoint, all right, is going to give me, when I plug it back into the function, it's going to tell me this length. So my length is going to be f of the midpoint. All right, so what is that midpoint? Okay, well, this distance in here we know is 1/3. All right, and I think we know that half of 1/3 is 1/6. Okay, so that means this midpoint right here is going to be 5/3 plus a 1/6, which is like 10/6 plus a 1/6. All right? So that midpoint x coordinate is 11/6. This thing right here is 11/6. And that is what I would plug into my function to find my length. My length is going to be f of 11/6 for that rectangle. So that would be e to the 11/6 power. And this rectangle right here would have an area of e to the 11/6 times 1/3. And then you would have to go through each individual rectangle and do that for all 6. Okay? And there are ways that we can speed this up using a program on your graphing calculator that I will give you later. All right? But right now we're trying to understand the process. So yes, I would still have 6 rectangles. This is one rectangle right here. Then I'd have to add it to the other 6, plus, etc. All right, I'd have to go through and do it for all of them. Now, we don't need to go through this problem all the way. This is the same problem we did a minute ago, but this is a right Riemann sum. So the only thing that changes, for example, on this first rectangle, the width is still 2, but my length, instead of using the left edge, I'm going to use the right edge. So my length would be 14. So the area of this first one would be 2 times 14, which is 28. And then on the next one, my width is 4, but my length is the right edge, which is 20. So that's going to be 20 times 4, which is 80, and so on. So when you're doing the right Riemann sum, you're using the right edge for each rectangle. All right? Now, if you see a problem like this, okay, they give it, if you can read that small lettering, the graph of the velocity is shown above, and we've got a table of values. This table matches up to this graph, all right? Approximate the distance of the car traveling using the midpoints of 5 subintervals of equal length, and notice it said midpoints, from 0 to 50 seconds. Okay? 0 to 50. So if we're talking 5 subintervals, then I'm going to do 50 minus 0, and I'm going to divide it by 5. So that's 10. That is the width of every rectangle. All right? But what I have to do now, this problem actually makes this kind of nice. Because look what they gave us. My width of every subinterval is 10. And my midpoint, that means my midpoint is halfway across that 10, which is 5. This problem looks challenging, but they actually saved us a whole bunch of flipping work because they gave us all of these midpoint values. The value at 5, f of 5 equals 12. That's going to be the length of that first rectangle. The width for all of them, we already found out, is 10. So that first rectangle, 12 times 10, is 120, and so on. And then we would go through and find the other 4 and add them together. All right? So this problem looks challenging, but because they gave me all of these midpoint values, it's actually much easier than the last one. Finally, trapezoidal Riemann sum. A trapezoid, okay, the area of a trapezoid is the average of the bases times the height. Now, another way I could write this is I could say this is h over 2 times, in here, base 1 plus base 2. That's a formula from back in the day that you may have forgotten. That's the area of a trapezoid. If you notice, a trapezoid would give us a much more accurate representation of the area if you look at the way those rectangles are drawn. All right? So what we have to do here is we have to average the bases, which the bases, here's the nice thing, the height is going to be my width of each rectangle. And we know how to find that. The width is the b minus a divided by n that we've been doing. That's the height, all right? But then that's going to tell me the height right here. These bases, however, are going to be f of the left edge of the rectangle. Okay, so I would say f of x1 plus f of x2. Those are the actual function values. All right? And so it depends upon how many trapezoids, but in this picture here, there's 1, 2, 3, 4. I would have to do this over here. I would have to do f of x sub 1 plus f of x sub 2 times that height divided by 2. I would have to do that 4 times. All right? And then we'd have to add them all together. All right? And you have to do it individually. And the reason we're doing it individually is because these function values here all change. All right? So let's kind of, here's our same problem again, but now we're told to do a trapezoidal Riemann sum. Okay? And if you notice, the problem, this is one of those that has the varying widths. Okay? So my height on this first one is going to be 2. All right? And if you remember, we're going to do h divided by 2 times f of x1 plus f of x2. All right? Well, what's my f of x1 here? My f of x1 is 10. My f of x2 is 14. And that's going to be multiplied by 2 divided by 2. So that's going to be 1 times 24. That is the first trapezoid. And then we would go through and we would do it for this trapezoid, and this trapezoid, and this trapezoid, and so on. And we will stop there for today on topic 6.2.